Assalamu alaikum students. I hope all of you are doing well, and today we will start our lecture from the topic 6.3, which is transfer characteristics. Last time in our previous lecture we have discussed that William Bradford Shockley invent the first transistor and formulated the theory for FETs. So later, based upon his theory, some other scientists and developers has established FET, and we are using a lot of FETs in our laptops, in our smartphones, and other electronic devices. So in this slide, as we have seen some similarities in transistor equation and Shockley's equation. The first of all, the transistor equation is IC is equal to beta IB, and the Shockley's equation is just like ID, which is a drain current. It is equal to IDSS and a factor like 1 minus VGS over VP square. So these two equations you can say are almost similar, but there is a different type of constant. In 6.2 the constant is just a beta, but in 6.3 we have a two type of constants, which is pinch off voltage VP and drain to source current. These two values will be fixed in our calculation in our numerical type questions. So we consider these two values as a constant, but we also have a controllable variable, which is VGS. So it can be changed. We can also change this variable according to our requirement. So here you guys can see a transfer curve which is divided in two parts. In figure 6.17 there are two parts of this figure. In right side we have plotted this graph between VDS and ID, and similarly in left side the graph is between VGS and IT. So let's have a more clear view of this graph. Now first of all, when we see the equation 6.4, which is VGS is equal to 0, then the drain current will be equal to IDSS. This point we have already discussed many times in type of figure, in type of equation, and in type of theory. So here it is also obvious that when we have VGS voltage is equal to 0, then the drain current will be equal to IDSS. So these type of questions can be asked from you in quizzes, or maybe in your viva. So you need to memorize these conditions frequently. The other equation which you can see in your screen is VGS is equal to VP, and we have set the VP is equal to minus 4 volt. The drain current is 0, and defining another point on the transfer curve, that is, if VGS is equal to VP and VP is equal to minus 4, then the drain current ID is equal to 0. In your screen, the figure 6.17 left portion, we can also observe that when the VGS is equal to minus 4, and that is equal to pinch off voltage, then the drain current we have taken this current on y-axis. So the drain current is nearly equal to 0, or you can say it is almost equal to 0. So this is also another condition, and we have given this condition as the name of 6.5 equation. So on the right hand side of this graph, there are different values for VGS, and we can see the different value of drain current. If we have VGS is equal to -4 volt, just like in left side, so the drain current is almost equal to 0. But the value of VDS, the drain to source voltage, is increasing. You can see 5 volt, 10 volt, 15 volt, 20 volt, 25 volt. So there is no change in current. Similarly, if we change the value of VGS, we can see there is a little bit difference in the drain current. So we have different value of drain current for different value of VGS. So here it is also observed that if VGS is equal to 0, then the maximum current will be obtained, and this maximum current is equal to IDSS, as it is observed from the graph. So I hope these two conditions is now very clear to you guys. So here is another part of this topic. We will apply the Shockley's equations of these two equations, and let's see what will be the results. So first of all, in equation 6.3, ID is equal to IDSS, and we have taken just a Shockley's equation, and we will put VGS is equal to 0 volt in this equation, and let's see what will be the answer. So according to Shockley's equation, we have found that if VGS is equal to 0, then the drain current is equal to IDSS. So it is proved now mathematically from Shockley's equation. Similarly, we have substituted VGS is equal to VP, and then let's see what will be the answer. If we substitute VGS is equal to VP, then the answer will be 0 in 6.7 equation. So the second point is also proved mathematically by using Shockley's equation. So here are two conditions. So if I ask from you guys that prove that if VGS is equal to 0, then ID is equal to IDSS. So you need to prove this condition by using Shockley's equation, and it is very simple. You can prove it in just 3 to 4 steps. So similarly, the second condition, like if VGS is equal to VP, then drain current will be 0. So you need to prove it by using Shockley's equation. So let's move to the next slide, and in the next slide we have another method, shorthand method, which falls in the topic 6.3. So here we can see some important points. Let's discuss that. We have already discussed the transfer curve in the previous slides, and if we specify VGS to be 1/2 of the pinch of VP, then we will check the final result. So you just need to change the values here, and you can see if the VGS is 1/2 of the pinch off, then the current will be reduced to the 4 times. So here you can also make assumptions of this thing. Here is the table 6.1, where VGS versus ID using Shockley's equation. Like if VGS is equal to 0, then ID is equal to this. If VGS is equal to 0.3 VP, then you will get IDSS by 2. And if you have VGS is equal to VP, then you will get 0 milliampere current. So this table is just like all the observations which you have made in previous calculation. So here we will move to the first example, the numerical example of this chapter. In this example, we have to sketch a curve defined by IDS is equal to 12 milliampere and VP minus 6. So we have known that the VP is minus 6 and IDSS is equal to 12. So we need to plot points are defined by this, and if IDSS is equal to 12, it means it is a maximum current, and then VGS should be 0. If ID is equal to 0, then VGS is equal to VP. So according to this equation, we can make this curve easily. We have known the final and ending point. Here you can see VGS is equal to 0 and VGS is equal to VP. We have final and end point, and we need to find just 2 or 3 points in the middle of this curve, and then we can make this curve easily. So here, first of all, if VGS is equal to VP by 2, then we will get minus 3 volt. The drain current is determined by like this, and we will have 3 milliampere. So at minus 3 volt we have 3 milliampere current. So we will draw these two lines like this. We will make a dot here. Then in the second part we will check that at minus 1.8 volt the current will be 6 milliampere, and we will draw a point here. Now we have 4 points, and we just need to join these points together, and we will find a curve by using these two conditions. If IDSS is equal to 12 and VP minus 6, and we can make a sketch of transfer curve. Similarly, there is an example 6.2, and we have to sketch the graph here also. So it is I think just like the same example, just the one difference is it is a P channel device. In the previous example there is a N channel, and you can see in the graph which is sketched after the calculation, the P channel devices have reverse behavior than N channel. So the curve will be at right hand side in P channel devices. So I hope this example is very easily to you guys, and you can solve it by yourself. So let's move to the next topic, which is specification sheets. As we have discussed this thing in our chapter objective, that we will study specification sheets in this chapter. What's the first thing comes to your mind if I discuss this, that I have a specification sheet of this device? So the first thing which comes in our mind, that the specification sheet is just a little bit knowledge of that device. Let's suppose if I buy some electronic device like a juicer from the market. So with that juicer I will get a handbook. In that handbook all the information is available, that how can I use this user in normal condition. So I will follow all that steps, and I will take precaution measures also, and the device which I have purchased from the market will work properly if I act upon all the precaution measures on that handbook. Similarly, if you want to buy FETs or BJTs or some other semiconductor devices, so you need to read out its specification sheet before using it. You need to determine that what conditions are normal for this device. So it's the first sketch about specification sheet which comes in our mind when we discuss about it. So in this topic, you don't need to memorize it like other topics, and you also don't need to have calculations, derivations here. Just there is a some information or some things which need to be clarified to you about specification sheets. So here is also you can see some physical devices. So you have the device like this which have very long legs, and you also have integrated circuit type devices which can be integrated on your PCB board. So every type of device is available in the market. So let's move to the other slide. So here is some specification sheets which I have taken the screenshot, some important things. The first one is some thermal characteristics is available on specification sheet. According to these conditions, we can check the thermal resistance junction to case will be this for this device, okay, 2N5457, and the unit which is used here is degree centigrade per watt. So these are the normal condition, you can say. Then there is electrical characteristics which are like this: off characteristics and on characteristics. The off characteristics like gate to source breakdown voltage will be this, gate reverse current will be this, gate source cutoff voltage this, gate source voltage this, and on characteristics is zero gate voltage drain is like this. So these are the normal voltages and currents for a device. You need to follow these parameters. Similarly, there are some small signal characteristics and absolute maximum ratings. So all these information are available in the specification sheet. So I think this information is enough for this topic. Some other things like maximum rating. Maximum rating list usually appear at the beginning of this specification sheet like this. So you have to clearly act upon on maximum ratings. If you exceed from maximum rating, then your device will not work properly. It may burn out. It will go to the breakdown state. So I also have highlighted here. So please, you do not need to exceed from maximum ratings if you want to work your device properly. These things I think are obvious to us. Then the thermal condition as the dissipation at 25 room temperature. Most of the devices will work accurately in the room temperature. And then there is a equation 6.11 which is PD dissipation power, I think, is equal to VDS and ID. Just the power formula, you can see voltage into current is equal to power. So here is like same. There is another thing which is discussed here is derating factor, which we have already discussed in chapter 3, but the moment to recognize that if 5 milliwatt per degree centigrade rating reveals that the dissipation rating decreases by 5 milliwatt for each increase in temperature of 1 degree C. Okay, if derating factor is about information that if 1 degree C temperature will rise, then the power or dissipation rating decreases by 5 milliwatt in every increase in temperature by 1 degree C. Again, electrical characteristics. So we will check the level of Vp in off state and in the on state. Similarly, IDSS also checked in these two conditions, and some typical characteristics are about that how important parameters vary with voltage, current, temperature, and frequency. In typical characteristics, these things mostly discussed. So the operating region, the specification sheet, and the curve defined by the pinch off level are defined here in the operating region, and here you guys can also see the locus pinch off level, which we have already discussed in the start of this chapter. In the basics we have discussed here. At IDSS we cannot exceed from IDSS, so we have the curves like this, and if we increase the VDS, there is also a condition for VD max, so we can VDS, there is also a condition for VD max, so we can go to this level maximum, and also we can go to the IDSS in y-axis. So between this portion or in this region, we can say the device or FET will operate normally in this region. Here also you can see the caption normal operating region for linear amplifier design. Okay, so just like some information from the specification sheet, we can draw this region by using the maximum values from specification sheet. So some in 6.6 topic, some important relationships are discussed here. The first one, a number of important equations and operating characteristic for JFET have been introduced in this section. To isolate and emphasize their importance, they are repeated in table 6.2. There is also a comparison with BJT and JFET in table 6.2. The first one, ID is equal to IDSS, and this so for BJT it is IC is equal to beta IB, and in JFET the drain current will be equal to source current, and similarly in BJT the collector current is equal to emitter current. In JFET the gate current almost equal to 0, and in BJT the base to emitter voltage, which is a diode voltage, is always equal to 0.7 volt if you use silicon semiconductor device. Okay, so in figure 6.3 we have the comparison, just like in JFET and BJT. We can see here in type of figure. Okay, the terminal names, direction of currents, and the equations and voltages. Okay, also you can say that the table 6.2 is represented in form of figure at your left side of screen. So a clear understanding of the effect of each of the equation, sufficient ground to approach the most complex of DC configurations. Okay, so we have now enough discussion that we can make the final remarks about this. So in BJT, if we recall that the base to emitter voltage is this, and was often initializing an analysis of a BJT. Before starting any numerical or any example or any calculation, we assume that the base to emitter voltage is equal to 0.7, and we will start our calculation. Similarly, in JFETs, we assume the condition that the gate current is equal to 0, and we will start our calculations. For BJT configuration, the IB is normally the first parameter to be determined. As you know, we have discussed many type of configuration, that a common meter configuration, common base, and base to meter, like this. And the first thing which we determine in that configuration is IB, the base current. If we find the base current, we can find all other parameters. Similarly, in JFETs, we normally determine VGS as our first parameter. So these are some summary type points about our whole discussion here, and I hope you will understand all these conditions, all these discussion, and the equations, the terms, the specification sheets which we have discussed in this lecture. So if further you have any question about this lecture, you can ask here by commenting on this video, and I will try to respond all of your queries. So we will meet in our next lecture. Till then, take care. Bye bye.